Okay, chapter 6 is on quadratic functions, and 6.1 is called Exploring Quadratic Relations. And in Math 1201 we learned about linear relations, so in this course we're going to be looking at quadratic relations. And if you remember, a linear relation had a graph that looked like a line. So what do quadratic relations look like? And in real life, not everything can be represented by a linear function, but a lot of things in real life do have a quadratic shape to them. And when we look at, for example, the path of balls that are thrown into the air, they would basically have this shape of going up and coming back down. And sometimes they would go down and then come back up. It might not necessarily be a ball, but like a rocket or some kind of if you imagine like a paper airplane or something that you let go of, go down and then sometimes swoop back up again. So anything that has that kind of a path is referred to or can be modeled as a quadratic relation. And the graph of a quadratic is called a parabola. And it basically, as we look at the two shapes we have up there, it's like a U-y shape or an upside down U shape or a smile or a frown. Quadratic functions can be found by multiplying two linear functions. So there's a connection to the linear relation that you did. And when you expand these here, using the rules that you learned in 1201, you have x times x is x squared, and then plus your 4x, plus the x, and then plus the 4. So y would equal x squared, put your like terms together, so 4x and x would be 5x, plus 4. And that's supposed to be a 2 there, it doesn't look like it. So the equation expanded form would look like this. It has an x squared term. Notice that it has an x squared term and a linear term, the 5x. And similarly, if you see something like this is a linear function squared. So when you write that out, that would be actually be 3x minus 2 by 3x minus 2. And that would give you, in simplified form, 9x squared minus 6x minus another 6x plus 4, which would give you 9x squared minus 12x plus 4. And again, I'm just using distributive property there like I did on the first one to get those values. So again, you notice that this one also has a squared term and a linear term. So in junior high, you talked a little bit about the degree of the polynomial, and that's the highest exponent in a polynomial expression. So the degree for each of these, if you look at them, the highest power for the variable would be 2. All right, so if we look at the equations and graphs here, we should see some patterns in how to identify quadratic functions. So the first two rows here are graphs with their corresponding equations written above them, and you have to categorize the functions, the equations above, by writing them under the correct category. So the first one, if we look at it, it has the pattern of a linear function, so that we would write the equation y equals 3x plus 1 in the first column. And then if we look at the other graphs to see if there are any other linear relations, we know that this one is taken care of. So this one here, y equals 2x, has that equation that looks like a linear equation. Remember, y equals mx plus b. In this case, the b would be 0. And it has a graph that looks like a line, so we know that that's a characteristic of a linear equation. And the last one that seems to be a linear equation is the y equals x. Because again, that has the equation that's a line, and it has the pattern y equals mx plus b. Again, b would be 0. So if we look at quadratics, we're looking for that U shape or upside down U shape, the smile or the frown. And we're also looking at, based on the first page of notes there that we had, we're looking at something that has an x squared in it. So if we look at the first equation, the next equation in the first row here, we have y equals x squared minus 4 has that shape of the graph of the parabola that we just talked about in the last page. So y equals x squared minus 4. And the other equation that has that shape, that parabolic shape, would be y equals x squared plus 5x plus 4. And the last equation that has that parabolic shape would be the last graph here, which is y equals negative x squared plus 2. So that leaves us with the ones that aren't linear or quadratic would be y equals 2 to the x and y equals x cubed. So now if we look at those equations, you can basically see that quadratic equations, every single one of them, had an x squared term in there. So when it's written in expanded form, a quadratic would need to have an x squared term in expanded form. Okay. So the next example basically asks us to look at the equations and decide which ones are quadratic. So sometimes you might not be able to tell exactly by looking at it, but if you expand, for example, this one would be y equals 5x plus 15. That does not look like a linear quadratic, sorry, it is a linear equation, not a quadratic. It does not have an x squared term. So this one would actually be linear. It's more like the y equals mx plus b format. Question number 2, if we look at it in expanded form, we have negative 2x squared minus 6x. So that, again, this one here, does have the x squared term, so this would be a quadratic. And example 3, if you expand, would also have the highest power being an x squared term, so 3x squared plus 9. So again, this looks like it has a quadratic form to it. And the next one would be 5x squared minus 10x plus x minus 2. And that would equal 5x squared minus 9x minus 2. So again, it has the characteristic 5x squared term, the x squared term being the highest power of x as a squared would be a quadratic. The highest power is 2. This one here kind of looks funny, but if you expand it as x plus 1 times x plus 1, you can see that when you expand this x times x as x squared, then plus the x, plus the next x, right, plus 1. And we're not really asked to simplify these, so you could actually stop there if you realize that this is actually going to be a quadratic as well, because you would end up with 5x squared plus the 5x plus another 5x, which would be plus 10x. And then plus this 5 has to be distributed to that 1, so that would be 5 plus the 2 that's outside, so be a 7. So this would be a quadratic as well. This one here, though, is a little bit tricky because the squared is actually not with an x, it's with a constant. So this here is not really an x squared term, it's a constant. And the highest power of x is just x to the 1. So this one would be a linear, not a quadratic. Question number 7. Again, if you're just looking at the first term, you would think it was a quadratic, but if you look through the entire equation, you see that it has a 4x to the power of 3 term. I've kind of covered up that 3 there now. So it has a negative 4x cubed term, so this would not be a quadratic. So it's not quadratic. And the next one, if you look through, there is an x squared term, and even though there's a power of 4, it's a constant. So that constant can be rewritten, and it wouldn't, the highest power of x that's there would be x to the power of 2, so therefore it would be a quadratic. And in the graphs, the only one that looks like it has a parabolic shape would be number 10. This is the only one that would be quadratic. You should be able to identify number 9 as a linear, and I wouldn't expect you to know the graph, what the graph of 11 and 12 are yet. All right, so first of all, we're going to explore quadratic equations in standard form. So we kind of know what a quadratic is and kind of what to expect, and the form that we're kind of using at this point is the standard form or expanded form of a quadratic. So if it can be written in the form of ax squared plus bx plus c, where a can't be 0, because if a was 0, then there would not be a squared term. And if it's not an x squared term, it implies it's not a quadratic. All right, so the simplest form of a quadratic that we're going to look at is y equals x squared. So if we take a table of values to kind of sketch that graph, we'll take a couple of negative values, 0, and a couple of positive values, and we're just going to basically square each of those values, because you just square the x to get the y value. So if I square negative 2, I get 4. If I square negative 1, I get 1. If I square 0, I get 0. If I square 1, I get 1. If I square 2, I get 4. 2 times 2 is 4. So when I plot those points, negative 2 with 4, negative 1 with 1, 0 with 0, 1 with 1, and 2 with 4, there's my rough sketch of a parabola. And I can't draw any better than that with this stylus, sorry. So if we look at the graph a little more carefully, you should be able to tell that the parabola is symmetrical. And it basically means if I look at this graph up here and I kind of split it down the middle, now my graph doesn't look exactly symmetrical because the way I've got it drawn, but if I split it down the middle, where this is kind of like your middle point right here, this is kind of the point that's on its own, everything else seems to have a match with it. There's one here, one directly across, one here, one directly across. But this line here down the middle acts as like a line of symmetry, where you could fold that was a piece of paper, you could fold it in half along that line, and this point would lie right on top of this point would lie right on top of that point, and so on. So this line that's cutting it down through the middle is called the axis of symmetry. And the point at which the vertex reaches its low point in this case, this is the low point right here, this is called your vertex. If the parabola opened this way, this would be your vertex. The vertex is referred to as a minimum if it's the lowest point on the graph, and it's referred to it as a maximum if it's the highest point on the graph. So when a graph opens up, it's going to have a minimum point because the vertex is going to be the lowest point on the graph. And if it opens down, the vertex is going to be the highest point on the graph. So it would be a maximum point. And we already drew the axis of symmetry for the parabola above. If you look back to see what the equation would be, it would be basically a vertical line that goes right through x equals 0. Because every single point on this line here that we're drawing, this is the axis of symmetry, goes right down through the vertex. And this would have an equation, x equals 0. Every single point on that line has an x value of 0. Every vertical line can be written as x equal a constant. So we know it goes to the vertex. It should have the same coordinates as the same x value as x coordinate of the vertex. So in our case, we said that the vertex, the axis of symmetry, was x equals 0. The vertex for that parabola above, if you look back, was 0, 0. X equals 0 and y equals 0 at that point. How would you describe the direction of opening? In that particular graph, it opened up. So we would expect it to have a minimum. All right, you should also be able to identify the domain and range for a given parabola. So if you got the picture, it's really easy to get the domain and range. You just basically look at it, what x values and y values are being used. So graph A is the graph here on the right. And if we look at that to describe direction of opening, I would say up. The maximum or minimum value would be the y coordinate of the vertex. So when we look at the vertex, we know that the y value for that vertex is -3. So the maximum minimum value would be, -3 would be, in this case, it would be a minimum value. And the axis of symmetry would be right down through the vertex. So that would be at x equals -4. And the domain would be, if you look at the x-axis, every single point on the x-axis has a point corresponding to it on this graph, because this graph is going to keep getting wider and wider and wider. So the domain would be all real numbers. And the range, the y's that get used start at -3, and everything higher than -3 has a matching point on that graph. If you look at all the y values on the y-axis, every single y on the y-axis, because the graph keeps going higher and higher and higher, would have a point on that graph. So therefore the range would be y greater than or equal to -3, wasn't it? Sorry, -3. And for graph B, this one opens down, and it has this time it has a high point, so that the vertex would be a maximum point, and the maximum value would be +3. If you look at the y coordinate that goes with that point, so 3 would be your maximum. And the axis of symmetry would be down through the vertex, cutting the parabola in half, and it would have an equation x equals 4. Domain again, the graph keeps expanding outward, so it would have all real numbers used, all values on the x-axis would have a corresponding point on the graph, but the range would only be y less than or equal to 3. So there's some questions there related to this now if you'd like to try those. But I'm just going to continue on with the remaining pages. There's an investigation that's kind of leading us into the next section, so I'll go through that with you. But there's some questions on page 324, numbers 1, 2, and 6AB that you can try. All right, so the next little part here is just basically an investigation of what the A, B, and C in the standard form of a quadratic equation y equals ax squared plus bx plus c. So what each of those does. So we're just going to look at first the a value. So when we compare y equals x squared to different graphs of the form y equals ax squared, first one we see that it has a is 2. And if you look at the red graph is the original graph of y equals x squared, and this one is y equals 2x squared. So when you look at this, if you had to describe whether it was narrower or wider, I would say that it would be narrower. And has it reflected across the x-axis? Basically, did the graph get flipped over the x-axis? No, both of them still open up, so we know. What happens when the a value is a smaller number, smaller than 1? Well, in this case, again, this would be your outside graph, the dark graph would be the graph of y equals a half x squared, and you compare it to the red graph, the original y equals x squared, I would say it would be wider, but still no reflection. Oops. And then if I do the last one here, the last one has the a value equal to -1. This one doesn't appear to have changed at all in the width, so no change. But it has reflected. So the negative seems to reflect the graph. And then if we combine the negative with the 2, in this case here, it still would be narrower, but reflected. And the last one, if there's a negative with the half, it is still wider. But again, because there's a negative in front of it now, it is reflected. So if we had to summarize that, we would say that if A is less than 0, it's going to be a negative, which means it's going to open down. And if A is greater than 0, that's a positive, it's going to open up. And if it opens upward, the vertex is considered a minimum point. And if it opens downward, the vertex is considered a maximum point. All right, so these are some questions related to what we just did with the A value. So the first question is the shape of the graph affected by the value of A, and are some graphs wider or narrower compared to y equals x squared? And yes, the answer to that question would be yes. So if A is greater than 1, you should have noticed that the graph was going to be narrower. And when we say A, we're ignoring the negative. If there's a negative, that makes it open up or down, but if the actual A value itself is greater than 1, ignoring the negative, then it will be narrower. And if the A value, again ignoring the negative if there is one there, if that value is between 0 and 1, the graph will be wider. And a way to help you remember that is to basically think, like for example, if you had A equal 2. If A equals 2, the y values are going to be normally x squared, now would become 2x squared. So that would mean they would be twice as high as what they used to be. So the graph should be rising or going up to the higher values faster, making it narrower. Whereas if you had, for example, the second one, if you had A equals a half, as an example, now you're taking half of the x squareds as opposed to just x squared. So if you're taking half of what you used to have for your y value, that means it's going to take a little longer to get up higher because your heights or your y's are only half what they used to be. So it's going to be a little bit wider than the original. So the A value tells you a couple of different things. If A is a positive, then A would be, or A greater than 0 being positive, that means the graph opens up and the vertex is a minimum. And if A is negative, the graph opens down and the vertex is a maximum. So if the magnitude of A, meaning ignoring the negative, absolute value of A, you basically ignore the negative. Absolute value of A would always be equal to the just the positive value of A. So if A is greater than 1, magnitude being greater than 1, the graph will be narrower. But if the A value is between 0 and 1, again ignoring the negative, the graph will be wider. So that's what happens when you look at the B value. So this one here, we're again comparing it to y equals x squared, and we're taking x squared plus 1x is the first one. And if you look at the graph itself, there doesn't appear to be it's hard to tell when they're graphed like that, but if you were to slide that black graph, the new graph, down on top of the original y equals x squared graph, which is in red, there wouldn't be any shape change. It wouldn't be narrower or wider. So there's no shape change. Is the vertex changed? Yes. And if you look at the second one, y equals x squared plus 2x, again, it doesn't appear to be any much wider or narrower than the original y equals x squared graph, which is in red. So there's no change to the shape, and the vertex is changed. And the last one, looking at a value of B that's negative this time, again, you can't see the full graph there, but if you were to extend the red one as high as the long, make the arms kind of as long as the black one, the new graph, y equals x squared minus 4x is in black, then when you look at those, again, there isn't a difference in the width, but there is a difference in where the vertex is. So what effect does B have on the graph? It seems to change the vertex around. Changes the position of the vertex. So, as summarized here, that the value B influences the vertex of the parabola as it changes the location of the parabola's line of symmetry. So, as well, because the vertex is changed, then the axis of symmetry, which goes straight down through the vertex, would necessarily be changed as well. So, if we're looking at the last thing we're looking at is the C value, which when you have y x squared plus bx plus c. So, what happens when we change the constant on the end of the equation? So in this case, we've got the y equals x squared is in red, and again, y equals x squared plus 4 is the black. So if you look at the change, the graph has shifted 4 units up. And this one, the graph has shifted, and the second one, when you subtract 3, you're basically taking the whole graph and it shifts 3 units down. And you can look at the vertex to see that this one was 4, the original was at 0, 0, now it's up 4. This one was at 0, 0, now it's down to 0, negative 3, so it's down 3. So what effect does C have on the graph? And it's hard to see in this particular case that it's always going to affect the y-intercept, because you're just looking at the vertex. It seems like it's just affecting the vertex, but the key thing with the C value is that it's affecting the y-intercept. Instead of crossing over at 0, 0, now it's crossing over the y-axis at 0, 4. So the C changes the y-intercept. That's the main thing that the C does. How we can determine that that's the case is because when you look at the y-intercept, you would let, in any equation, if you want to find the y-intercept, you want to find where it crosses the y-axis, so you let the x-coordinate be 0. And if you plug 0 into this, you get a times 0 squared plus b times 0, because you're filling in x with 0. So then that just simplifies to 0 plus c, which is c. So no matter what, if you plug in 0 into any equation, no matter what a and b are, you'll basically end up with just the value of c. Is the axis of symmetry affected by C? And the answer to that would be no. Now, when you take an equation and you've got A's and B's and C's changed, then obviously the vertex would move and the axis of symmetry would move, but it wouldn't be affected by the C. It would be the B value that's affecting it. All right, so the value of C influences the y-intercept of the graph, and in standard form of equation, when you have the standard form of equation, these two, when you plug 0 in for x, these two terms will always disappear, leaving you with just the C value. So therefore, if C is positive, you're going to have a y-intercept that's positive, and if it's negative, you're going to have a y-intercept that's negative. So we're going to look at this table down below now and see if we can kind of put it all together. And the first one asks you to determine the direction of opening. So the direction of opening would be affected by the A value. So this one, the A is negative, so it's going to open down. And if it opens down, then it's going to have a maximum value. And the width of the graph, whether it's wide or narrow, depends on, again, the A value. Ignoring the negative, that would be an A value of 2. So that would be bigger than 1, so that we're expecting a graph that's narrower. And the y-intercept would be y equals negative 1, because when we plug in 0 for x's, the first two terms disappear and you're left with just the C value of negative 1. The second one has an A value. The A value is what's always in front of x squared, right? A x squared plus b is in front of x, and c is your constant. So this one, the A, is a positive, so this one would open up. And then because it opens up, it has a minimum value. And it would be wider in this case because the A value is a half. So the y's are half what they used to be, so it's taking a little longer to get up higher, so it's going to be a wider graph. And the C value is going to be the y-intercept, because when you plug 0 in, you'll end up with y equal 3. The next one has, now, if you look at this one, the first term is not the a value. The first term is actually the b value is -4. A is actually the one that goes with x squared. So this x squared term, this equation is not written in the proper order. So we just have to be careful that we look at the right term. So a is equal to 3 in this case. So that's a positive 3. So that means it still opens up. It would still have a minimum value. And it would be, in this case, 3 would make it narrower because the a value is bigger than 1, so it's going to be a narrower graph. And the constant term in this example is -5. So that would be the y-intercept. And the last one, again, the terms aren't written in the proper order. So if you look at what's in front of x squared, it's a positive 1/3. So it's going to open up. It's going to have a minimum. And it's going to be wider, though, because the a value is 1/3, which is less than 1. And the y-intercept will be the constant. So if you plug 0 into that equation, you're going to be left with the constant 8. So it should be crossing over the y-axis at 8. And here are some other questions you can try on page 324 to help practice these concepts that we've learned.